All right, let's go ahead and get started. I announced earlier that I'm not going to do a quiz today. I'm going to just wait till, what, Tuesday? So I would expect one on Tuesday. That way you have the whole weekend. I know you're not just going to sit around and do pre-cal all weekend. So, yeah. We'll pick up. We got more work to do in 7.1, and then we'll get into 7.2 today. And I'll go ahead and pass the sign-in sheet around. I'm also, in this folder, I'm going to pass around the stack of quizzes. Is everyone okay with me just passing these around? Anyone have any objections to that? You do? You object? Okay, then I'm not going to pass them around. I'll have you come pick them up. Okay? Yeah, that's fine. So, but you can do that at the end of class. Just don't forget they're up here. Alrighty, questions over anything before I begin? The main theme of last class was to, you okay? Okay, you look like you were gonna. The main theme from last class was trying to get you to understand the difference between degrees and radians. And then the other main theme was trying to get you to understand that way that we can count around and get an infinite number of angles using that k or that n. And then we started getting some other formulas at the end. I'm going to start today by talking about the common angles, and then we'll get back into the formulas that we were working with the arc length and area of a sector. So common angles is where we're going to begin. So when it comes down to angles, you could say there's an infinite number of angles within even just one full revolution. There's an infinite number of angles. And there are some that we need to know, we need to memorize, and they will become very useful to us later. And they are as follows. So imagine that we take, again, our standard position, and then we kind of throw this onto the XY coordinate system. So we have got our XY axis like that. Since there are 360 degrees in a full revolution, naturally cutting it halfway would be one important angle. We already talked about that. That would be 180 degrees. So this right here, I'm just going to label the ray. That's 180 degrees. This would be 0 degrees. And then if we cut this in half, we have 90 degrees. If we look at the ray that points straight down, that would be how many degrees? It would be the 180 plus another 90 degrees. So each kind of L shape is a 90 degree, right? So we have 180 plus 90, that gives us 270. And then, of course, if we come all the way back around, that's 360. So there's four of your common angles. The next group is going to come from cutting the 90 in half. So if I cut 90 in half, I have this very important angle. Half of 90 is 45 degrees. And then if I add 45 to 90, I get 135. Then if I add 45 again, I get 180, and then 45 again. What would I get down here? If I add 45 there. 225. And then finally, over here, if we add 45, we're back to 270. And then back over here, we are at, or here we're at what? 315. And then add another 45, we're at 360. So now we have, let's see, a total of, we had 4 blue ones, and now we have 4 red ones. So we're up to 8, right? 8 common angles. Most of you have seen something like this before, and this isn't news, and I'm already boring you today. But again, I want you to try and visualize this a slightly different way today. 0 degrees. If I move from 0 degrees to 45, I'll be here, right? That's 145. That's a rotation by 45 degrees. That's one rotation by 45 degrees. This is 2 rotations by 45 degrees. This is, what, 3 rotations, 4 rotations, 5, 6, 7, 8. Agreed? So we're not going to do this, but I want you to just understand, you could write this as 45 times 1. This could be 45 times 2. 45 times 3 times 4 times 5, right? I could do that. Now that's useful to us when we try and visualize this stuff in radians. It's useful to think about that sort of counting, as you'll see in a second. But we're not done with the common angles. The other common angles that we're going to work with are, what we do is we take, let's say we'll take this 90 degrees right here and we'll cut it into 2 equal sections, which means that we'll have 30 degrees and then 60 degrees. And I want you to look at those green ones, and I want you to, again, think about them as you can count your way around the circle. So this is 0. This is 130, right? This is 2 30s. Where's 3 30s going to be? Where's 3 30s? Straight up, right? 90 degrees. But we already have that one, don't we? That's one of our common angles. But I'm going to put a dotted green line here to help you see. 1 30 degree, 2 30 degrees, 3 30 degrees, 4 30 degrees will be, somewhere in here will be what? 120. And then right here we'll be at 150. Next one would be 180, right? That's where we would be. And then 30 more, 210. Then where? We're adding 30, right? I'm hearing like 4 different things. 240? Okay, 240. And then where would my next one be? Straight down, right? 270? I'm just adding 30 degrees every single time, right? Okay. So there I'm at 270. Add 30 again. 300. Then the next one would be 330. And then we would be back to 360. Now the reason why I separated the green ones from the red ones and the blue ones from the red and the green is because, again, this whole idea of counting. If you want to go and move along the blue ones, you're just going to be adding multiples of 90. So this would be 90, 2 90s, 3 90s, 4 90s, right? Red ones, 45, 2 45s. I guess I should have put 2 45s would be straight up here. The 45s land on the blue ones, don't they? They also land there. So 45, 2 45s, 3 45s, 4 45s, 5, 6, 7, 8. Yes? And then the green ones, you're counting by 30s around. That's a lot of angles to remember, right? But those are the common ones. So you need to know when someone's like, oh, 300 degrees, you need to know kind of where you are, all right? First quadrant, second quadrant, third quadrant, fourth. So that's all the nice common angles in degrees. Let's do the same thing in radians. This is where things can get a little weird. But I think maybe with the way I've done this to start, maybe you can see how I'm going to do it. All right. So let's start with the blue angles. This first blue angle in radians, this is radians. And then this was degrees. So that would be 0. Straight up would be what? Well, maybe let's start, what's straight across? Pi. It was pi, right? Straight across was pi. So that's pi radians. So if I go straight up, that's half of that. Half of pi? So pi over 2. Half of pi would be pi over 2. So pi over 2 is kind of like the 90 was, right? We did 190, 2 90s, 3 90s, 4 90s, right, to get around the blue ones? Please try and think of it that way. Let me say that again. 0, 90, that's 190. 2 times 90 is 180. 3 times 90 is 270. 4 times 90 is 360. So if this is kind of like my key angle here, this is 0. This is 1 pi over 2, right? This should be 2 pi's over 2, shouldn't it? And the 2's would cancel, and that's where you get the pi, right? And then you go one more rotation of this, and you would be down here. How many of them have you done now?
3.
That's your third rotation. So this is your 3 times pi over 2, and that's just 3 pi over 2. Multiplication, when you say 3 times pi over 2, that's the same as 3 over 1 times pi over 2, and you go 3 pi over 2. Do y'all see how I'm getting this? All right. And then when we come back around to up here, right, we've done, this is our what? Our fourth one, right? So we go 4 pi over 2, but that's actually just 2 pi. Okay, and then also it's 0, right? You can say that. So you see how I counted? I think, in my experience, it's much easier to think about these radians in terms of counting your way around than it is to try and memorize this big old massive table or chart of angles. Because you can create the whole circle this way if you just think about counting. All right, so now let's go with the red one, the 45s. And the 45s were half of the 90s, right? Which means that the 45s over here are going to be half of this. And what's half of pi over 2? Pi over 4, right? Let me erase this. If I take that and take half of it, I'm multiplying it by a half. Straight across, you get pi over 4. Pi over 4. So this is pi over 4. Okay, now I'm going to count my way around. You ready? This is 1 pi over 4. 2 pi over 4. I'm just going to write down what that would be. What's 2 pi divided by 4? The 2's would reduce out. You get pi over 2, right? That's where I am, okay? But this next one would be what? I'm on the third one. So I'm at 3 pi over 4. Next one. 4 pi over 4. The 4's would cancel, right? If I had 4 pi over 4, the 4's would cancel. I'd just be at pi, which is where I am. So that's reassuring. Next one. 5 pi over 4. Then this one should be my sixth one. And what is 6 pi over 4 if you reduce the fraction? 3 pi over 2, which matches up with what I had there already, right? So I had one here. Sorry, I forgot to put these here again. I'm on my sixth one. Now I move to the seventh. Right here, 7 pi over 4. And finally, back up here, 8 pi over 4, which is 2 pi. Do y'all get that counting way? All right. Now let's take care of the 30s. So I want you to try and focus your attention back here for a second. Here was 180 degrees, right? If I look at these 30s, I took 180 degrees, I cut it into 1, 2, 3, 4, 5, 6 sections, didn't I? 6 equal sections. So what I can do over here is take this rotation from here to here is pi. To cut it into 6 equal sections means I'm going to have to take that and divide it by 6. So I'm going to be starting with pi over 6. And that will be equivalent to my 30 degrees. Pi over 6. That's one of them. 2 of them should put you here. And if I have 2 pi's over 6, that's really what? Pi over 3, because the 2 and the pi, the 2 and the, I just erased, I'm wrong. The 2 and the 6 reduce out. So this should be pi over 3. Okay. I'm going to count again. I'm going to be on which one now? Pi over 2. Yeah, but I'm on the third one, right? The third. So I started at pi over 6. This is 2 of them. I'm at 3 pi over 6 straight up. And what would 3 pi over 6 reduce to be? Pi over 2 again, okay? Now I'm going to move to the fourth one. So this one's going to be 4 pi over 6, which reduces to be 2 pi over 3. The next one will be 5 pi over 6, should put me here. The next one should be 6 pi over 6, which should put me back here on the x-axis. And 6 pi divided by 6 should just be pi, so again that matches up. Next one, 7 pi over 6, that does not reduce, so I'm just going to leave it as 7 pi over 6. Then this one will be 8 pi over 6, but that reduces. 8 pi over 6 reduces to become 4 pi over 3. So that's the 8th one. 9 pi over 6 would be here. And 9 over 6 reduces to be 3 over 2. So that matches. Almost there. Which one am I on? 10, right? So this one right here is 10 pi over 6. 10 pi over 6 reduces to be 5 pi over 3. So 5 pi over 3, one more. What, 11 pi over 6? That was the 10th one, now I'm at the 11th one. 11 pi over 6. And we could do, the last one would be 12 pi over 6, which would just be 12 over 6 is 2, so 2 pi, so we're back there. People's brains work different ways. I'm not a person who likes to memorize things. My brain doesn't work that way. I'm not good at memorizing things. If I understand how to make that circle myself, I'll never forget it because I understand how to create it. So throughout this class, as we move on and we're talking about, hey, you know, where is, can you tell me where 18, no, that's no good. 17 pi over 6 is? Oh, let's go negative. 17 pi over 6, like where is that? Well, there's all sorts of ways you could do that, but one kind of easy way to do it is just to realize it's negative, which means that it goes clockwise. Just count your way around. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Get the idea? 12, 13. Where am I? 14, 15, 16, 17. There. It's equivalent to that. So, I mean, you can count your way around the circle pretty easily if you understand how that was all generated. All right. Good? Those are the common angles. We will be using them. And we learned last class how to convert from one to the other, didn't we? We did? We did the conversion factors? We did. I gave you the conversion factors and said, you know, here's how you convert. Oh, man, thing doesn't want to erase. I have a student in my Calculus 1 class right now that I won't get into too many details, but I asked them a question and something that they should have known from pre-cal. Something like what should be like a 1 plus 1 problem for you right now, like what's 1 plus 1 it's equal to 2, right? It was a very basic pre-cal question they didn't know. And then we were messing around trying to figure out an angle, and they started doing some weird thing with their fingers and trying to like they had memorized those angles off of their fingers or something. Anyway, there's different ways that people teach how to remember those angles. I'm trying to give you a way that I think is most constructive, makes you think kind of a different way. Hopefully it helps you. If not, hey, memorize it. All right, I'm going to move on. We were talking last time about arc length. Remember that? We're talking about arc length? Okay, there's another formula that we did not talk about last time that I said we would, and that's the area of a sector. And I'll remind you from last class that the arc length was the formula S equals R theta, and that went with this picture. Slice of pizza, R theta S. So if you want to know the length of that curve, you just need to know the radius and you need to know the angle. And there was something special about the angle in here, in this formula. What was the special that you can't forget or else it's going to mess it up? What about that angle? Has to be in radians for this to work, okay? Same with this formula, area of a sector. We still have the same picture. We have that little slice of pizza, we have R, and we have theta, but this time we're trying to find the area. We'll call that A. And it's equal to 1/2 R squared theta. That is different than this, right? Right here, S is that red part right there, that length. This is area, which is, area is a measurement of like how much paint you would need to paint that. Length is like how much, how much fence would you need to, to cover from one point to the other. Totally different measurements. So there's your formula. Again, I'm not going to derive the formula for you. That you're just going to take it on faith, all right? There it is. Now this formula might look familiar to you. Maybe. If I give you a circle and I give you its radius, do you know what the area of the circle is? What's the area? What's the formula for the area of a circle? Do you remember it? Area equals pi, I heard it, pi r squared. Okay, that's the formula for the area of a circle. What I want you to see is that this formula actually comes from this. How could you create an entire circle in this from this problem right here? How do I create the entire circle? What do I need theta to be? I need theta to be 2 pi, don't I? That'll make it come all the way around. And then the area of that, if I plug 2 pi right here, what happens? Yep, that's supposed to be 1/2, and then it's r squared, and then you plug in 2 pi for your angle. These twos cancel, and you get pi r squared. So again, this is a more general formula than this one. This is a specific example when you go all the way around. All right, so let's actually find the area of a sector. Give you an example. Let's say that we have a, we'll just do this one very mechanical, no word problem here. I'll just give you a sector. Let's say that this is 120 feet measured out here. And let's say that we have a way of measuring this angle and it's 30 degrees. 2 questions. Part A, find arc length. Part B, find area. And we definitely do not want to overcomplicate this problem. This is very much just plug in, go. Yes?
Does it have to be in radians?
It does have to be in radians. I didn't give it to you in radians though, right? I did that intentionally. So for part A, what formula am I using for part A? Arc length. So S equals R theta, right? But theta has to be in radians. So let's convert 30 degrees to radians. It's pi, this one right here. This is one of your common angles, isn't it? 30 degrees on your circle that we just drew is also the same as what? Pi over 6. It's pi over 6. What if I gave you some weird angle like 35 degrees? You'd have to convert it. So let me remind you of how we convert. I'm going to convert 30 degrees. To convert 30 degrees to radians, I use the conversion factor that we talked about last class. The conversion factor for this is pi over 180. That I would multiply by 1. Do y'all remember me multiplying by 1? This was the conversion factor. And what happens is you get 30 over 180. That reduces out to be 1/6. So this becomes pi over 6. But it's better for you to realize that 30 degrees is equivalent to pi over 6 off of our common angles to understand that. All right, so we're there. S is going to be equal to the radius, which is 120 feet, times the angle, which is pi over 6. And that's the same as 120 pi divided by 6 feet, which is really just 20 pi feet, right? Six goes into 120 20 times. And now, if that would be what we call our exact answer. This is an exact answer. Exact meaning I'm not doing any rounding. There's no approximation. This is exactly what it is. Now, if we wanted an approximate answer, then what we need to do is get on our calculators and do 20 times pi, and I'm sure your calculator has a pi key on it. And go ahead and someone do that. You should get something around 628. Anyone getting that?
I got 62.8.
62, sorry, yeah, 62.8 or so feet, right? 62.8 feet is approximately. So we use the squiggly equals to say approximate. So the squiggly equals means like kind of, like kind of close to that. But it's actually a real mathematical symbol. It's not like something that, like if any mathematician would accept that as a good symbol. All right, it's not. I always thought someone was just trying to be clever using a little wavy equals, and it was just trash. But it's actually a legitimate mathematical symbol. All right. Okay, so there it is. There is a huge difference between an exact answer and an approximate answer. Because your approximate answer stops around, like at some point you have to round, right? And so you can lose precision, and it can create a lot of problems. That little small approximation could be amplified if an operation is done in a problem maybe 20 times and you're rounding each time, you can create a huge error in the problem. So a lot of engineers have to be very careful about when they approximate, how far they go, how many significant digits they want to use, all that stuff. So the exact answer is perfect. I mean, that's exact. Problem is, what is 20 pi? It's hard to understand. So that's more concrete. We can visualize what 62.8 feet looks like. So that's the length. That's this length right here. Next question, part B, is to find the area. So we're going to just kick out that second formula, which was 1/2 r squared theta. And that'll be 1/2. We've got a square 120, don't we? Got a square 120. And you could put the feet in there, couldn't you? I'm going to leave the feet off on this one. On this one, I put feet through the whole computation. This one I'm not, because I'm going to look at it a slightly different way. And then I'm going to take that and multiply by pi over 6. So calculator time. What's that? 14,400 divided by 2. So I squared 120 and then divided by 2. And I'm getting 7,200 times pi over 6. I haven't multiplied by pi over 6 yet. I'm going to divide that by 6. Ooh, it's a nice number. 1,200 pi. Which is approximately 3,769.9 something. So here's my exact answer. Here's my approximate, but I'm missing my units. I didn't put my units in here. And what are my units? Feet? Feet squared? What do you think? Feet squared. Because, remember we had 120 and it was feet? And we squared it? That gives you your squared unit. But more importantly, it's area, isn't it? And area is measured in squared units. So we need to keep that in mind, that this is square feet. Square feet. All right, last topic of the section has to do with an object traveling in a circular path. All right, so we're going to kind of switch gears here now. Okay, objects traveling in a circular path. And before I get too deep into this, let's talk a little bit about speed. You've heard the word speed before. Speed is defined to be the distance you travel divided by the time it takes you to travel that distance. Now I need to clarify something. With speed here, this is actually average speed. Your average speed is the distance you travel divided by the time it takes you to travel that distance. So if I go run across this room and it takes me 3 seconds and I travel 30 feet, then what was my speed? What was my average speed? 30 feet across the room took me 3 seconds. So I'm going to take the distance I traveled, which is 30 feet, and I'm going to divide it by the time it took me to travel, 10 seconds. And my average speed is going to, what was it? It was 3, right? 3 seconds? I'm fast. I'm not that slow. Okay. So that, 10 feet with a little slash per second. So it's 10 feet per second. Okay? I'm quick, man. I'm telling you. Yeah, 10 feet per second. Is that fast? Is 10 feet per second fast?
If you're striding, maybe.
What is the measurement of speed that we're very comfortable with? In terms of if I tell you speed, what's the speed that you're comfortable giving me a good answer, in terms of? Well, let me say this. If I run at 450 feet per minute into a brick wall, am I alive or am I dead? 450 feet per minute It's not something you can just like, oh yeah, I get that. Now if I say I run into a brick wall at 60 miles per hour, am I dead? Yes, because we deal with 60 miles an hour. You know what that feels like, right? You know what 60 miles an hour feels like. 10 feet per second is not something that you're very comfortable with because it's not a unit we use that often, right? So how could you figure out what this is in miles per hour? I'm going a little bit off topic, but we may as well just practice a conversion real quick. 10 feet for every 1 second is what that means. I would love to get us to, at the end of the day, miles over hours because that's something we deal with on a daily basis. So what I have to do to do this is multiply by a bunch of ones. And these are my conversion factors. So let's first talk about how do we get feet over to miles. Do you know how many feet there are in a mile? 5,280. Now, you might have to Google that, but if I was going to Google anything, I would just say, convert 10 feet per second into miles per hour, and it'd be done, right? Okay, but we can do it mathematically like this. There are 5,280 feet in 1 mile. So what I'm going to do is put 5,280 feet here on the bottom and 1 mile on the top. Why did I put the mile on the top and the feet on the bottom? So that these feet cancel. Okay, that'll take care of that. Now, I need to take care of seconds. So how many seconds are there in an hour? There's 60 seconds in a minute and 60 minutes in an hour. So you'd have to multiply 60 times 60 and get 3,600. And where do I put the 3,600? On the top or the bottom? Top. 3,600 seconds in 1 hour. And now the seconds cancel. That's why we put it on top. So if you multiply 10 times 1 times 3,600, right? And then divide that by 5,280. You get about 6.8. 6.82 mph. I'll write mph because that's the way we like to write that. So if I'm running at 10 feet per second, I'm really running at almost 7 miles per hour. That's pretty fast. But if I hit a brick wall at that speed, I'm okay, I think. Depends on how I hit it, right? Yeah, might be a concussion.
You do the same thing with like try to calculate how fast people run on track, like the Olympics and stuff. You do the same thing.
Are you asking me?
Yeah.
Yes. The difference between someone running on a track versus someone running in a straight line is that they're running around a curve, right? And if they're running around a curve, then the distance they travel is different than the straight line distance, right? So if I go from that wall to that wall, I can measure a straight line 30 feet. Took me 3 seconds. That's my speed. But that's exactly what this is about. What about objects traveling around a circular path? Now in the Olympics, it's not a circle necessarily. Yeah, it's almost like an oval. It's more like straight, curve, like that. So like between here and here, it's just regular old, distance divided by time. But along this curve, like this, you actually have to imagine taking this curve off the paper, straightening it out, and that's your distance, right? What's that?
400 meters for a whole thing, so the curve is still...
I thought, well, yes, if you're just talking about getting from here back to there, you know the total distance. And you just divide it by the time and you're done. Yes. But I thought we were talking about like if you wanted to find the speed of a runner that just like from there to there. That's going to be different because you need to know what that distance is, right? So this is actually leading me right into what we're doing here. If speed is distance over time, then if we go around some path that's circular, we need to know that distance, don't we? But what is that? What if I take a circle and I take just part of it?
over 4.
Well, yeah, it'll depend on the angle. But imagine, let me blow this up. So if I have a runner or something, I have a circular path, right? And I have some person or whatever, some object that is, why did I pick up blue again? Some object that is going to move, let's say from this point, they're going to run around like this, and they're going to get to here, and I know the time it took them to do that. Then what's their speed? Well, I need that distance, don't I? I need the distance, that black curve. I need the length of it, don't I? Well, we have a formula for that length, don't we? The formula for that length requires that we have the radius and this angle, right? We know that this piece right here is r theta. Theta has to be in radians. So what would the linear speed of an object traveling around a circular path be? What would the speed be? We call it linear speed, even though it's not a line. It should be equal to the distance I travel. What's the distance I travel? S divided by the time it takes me to travel, right? Which is t. Time, whatever time is. Do you all agree with that formula? The linear speed should be equal to s over t, but that's just r theta over t, isn't it? Where did r theta come from? Well, that's what s is, right? Now, the book uses, for speed, they use a letter. They use the letter v. Now, the problem with v is this. What does v stand for? Velocity. Has anyone here taken physics before? There's a difference between velocity and speed. Okay, so in physics you learn, and even in later calculus classes, you learn that, and we'll talk about it here too, we'll talk about vectors, but velocity is a vector, speed is the length of that vector. But in a class like this, we'll be okay with just using velocity without any sort of confusion because we haven't talked about vectors. So, and they don't want to use s for speed because they already are using s for arc length. You run out of letters, man. We only have 26 to work with, all right? Okay. That's the formula for linear speed. Let's do an example. A runner travels 3 times around a track in 20 minutes. The track has, the track is a circle of radius 230 feet. Find the runner's velocity. Do we have an object moving around a circular track? Yes. We are asked to find the velocity of the object that is running around the track. The velocity is the arc length over the time it took. The arc length is r times the angle. Do you know the r times the angle and then divide by time? Do you know the radius of the circle? Yes? So I'm going to start putting this formula together. Its radius is 230 feet. I'll keep the units in there. Times, now here's the part that I guess you can kind of get a little bit messed up on. What's theta? 6 pi? Where are you getting 6 pi from? Yep, the runner ran 3 times around the track, right? So the first time went around 2 pi, then 4 pi, then the third time around would be 6 pi. So this angle here is like a total angle, right? It's not the angle, you know, that you started at and then you end, because the runner starts, let's say at this point right here, goes around 1 time, 2 times, 3 times. You're not saying that your angle is 0 because you ended up here. You have to look at this total measurement. It's like 0, and then there's 2 pi, and it keeps going. That's 3 pi, now it's 4 pi, then it's 5 pi, now it's 6 pi. So this is going to be 6 pi. Any questions on that part? Over 20 minutes. And now compute. So I'll get my calculator here. I'm going to go ahead and give you the approximate answer. So 230 times 6 times pi. And I'm going to divide that by 20. I'm getting approximately 216 what?
Feet per minute?
Yep, points. Let's go with 0.7. You could go 0.8. It probably rounds 0.8 better, but 0.8 feet per what? Minute. And of course, you could convert that to miles per hour, but I'm not asking you to right now, okay? Does that seem fast or slow?
A little bit too fast.
Too fast?
I'm not sure that's a walk.
216 feet. How long is a football field? 100 yards. A yard is about 3 feet. So that's like less than a full football field, right? In 1 minute. That seems fast or slow? Let's ask Google. I'll ask Google, sir. Okay, Google. Convert 216 feet per minute into miles per hour. 2.4 miles per hour. 2.4 miles per hour. That's pretty slow. That's pretty slow. That's maybe a fast walk. I don't know. Well, I didn't tell you, you know, this is a 97-year-old man. He's lucky to be out there. All right, understand? Okay. Now let's move on to the next formula. That was linear speed. Sometimes we're interested in something else. Imagine that you're the poor coach for this 97-year-old man trying to train him, right? And you're standing at the center of the track, the center of the circle. And it's very important because he's so old, you have to, be constantly watching him because of his health. So you're sitting there and you're watching him go around this track. Right? As you're turning, you can imagine that you're actually sweeping through an angle, aren't you? And there's a certain speed at which you're doing that. It's not like you're like, he's slow. So it's almost like the second hand on a clock moving, right? And so you go through a certain angle in a certain amount of time, and that is called the angular speed. So we need to have an understanding of how we could compute an angular speed. So angular speed is equal to theta over time. It's a very straightforward formula. It's the angle that you sweep through divided by how long it takes you to do it. Now we have a special letter for this. Like, remember how we had S for arc length? For angular speed, we use omega, Greek letter. omega. It almost looks kind of like a W. So if you look at velocity was distance over time, right? Angular speed is not distance over time, but angular measurement, which is almost like a distance, but it's an angle measurement divided by the time. Now with this formula, we actually can create a new formula. Check this out. Remember velocity was r theta? Remember that formula from earlier? We just did that? Can you solve this for theta? What would it take to get theta by itself on this equation? Multiply both sides by t. So would you agree that theta is equal to omega times t? Yes? Now come back into this formula and replace, oh wait, hold on, I forgot something on velocity. What did I forget? Divided by t. Oops. I gave you s. I was having a brain fart there. Velocity is s over t, so it's r times theta over t, yeah? Okay, now replace theta with omega t. And you get r omega t over t, and you just get r omega. So this is a second formula for velocity, for linear speed. If you know the radius and you know the angular speed, you just multiply them together and that's your velocity, your linear speed. Let me show you an example of this, all right? There are two formulas I just gave you. Omega is theta over t, and v is now r omega. So this is probably the first time I'm going to demonstrate my artistic abilities in here. I always tell my students when I start drawing things to not be intimidated by my level of skill here, okay? Because it's intimidating. I understand that that's obviously a truck, okay? And I just don't want you to be like, man, he's good at drawing. I can't draw like that. So y'all okay? You get the idea? There's a truck. This truck is moving along, and it got this rock stuck in it, in the tire. In the tread of the tire, there's this little rock. Okay? And that rock is sitting there going, right? Going around as the truck goes around. Does anyone have an idea of what the path of that rock looks like? This is a stretch. I wouldn't expect you to, but if you could like zoom out and just take the truck out, take the tires away, and just what would the path of the rock look like from the side? Like it's moving, just the rock. Up, like what? Up and down? It would actually look like this. That's what the path of the rock would look like if that truck was driving. So if you have a rock stuck in your tire, it's constantly going like up and down and up and down. That's what it's doing as it's moving that way. Because the truck's moving. So it never goes backwards. I know, look. Next class I have an animation that I use in my Cal 2 class that shows an actual wheel turning with the rock moving in it and stuff. Because we actually try in Cal 2 to figure out what's the function that does this, and there's a specific function that does it. It involves trig functions, but we haven't even talked about them yet. So anyway, okay, let's get back to this. We won't argue about that right now. So this truck's moving along, right? I mean, this thing's spinning, all right? Now, I'm gonna simplify this problem. I just want to know right now, if you just imagine the truck's not moving, but just the wheel is spinning, I want to know how fast that rock is moving, okay? How fast it's moving. Okay, but I need to tell you how fast the wheel's spinning, right? Okay, so I need to give you some information here. Truck wheel, or I'll say truck tire, spins at, let's go with 350 RPM. What does RPM stand for? Rotations per minute. That wheel's spinning at 350 rotations per minute. Tire has a 20, no, 20 is too big. Let's go with a 10-inch radius. A 10-inch radius. All right. Find, you can't tell that's a monster truck? 10-inch radius, I don't think that's
20,
that big.
We would have went with 20, yeah.
20 would have been pretty big, yeah.
40-inch.
Find tires 10-inch radius. Find the linear speed of the rock. Now, because I do record my lectures, I just want to be clear with you that this question that I'm asking you does not match up necessarily with this picture. If the truck is moving, this rock is actually doing that weird thing, and its linear speed is different than what I'm asking you to do. We're almost imagining that this truck is like jacked up and the wheels are spinning, okay? Because it's just staying in one spot. But I, again, wanted to show off how good of a drawer I am. Okay, here we go. So you got two formulas for linear speed, don't you? You have velocity equals r theta over t, and you've got velocity equals r omega. Those are your two choices. Both of them you've got r, don't you? You've got the radius. So this right here is r. You're good. What is this, though? 350 revolutions per 1 minute. It is a lot of pies. But 350 revolutions per minute, is that a measurement? It's something over time, right? It's angular speed. It's the 350 rotations is telling you about an angle, isn't it? And this is how often it's doing it. This is your time. So this looks like omega, doesn't it? But 350 revolutions is not an angle in radians, right? It needs to be an angle in radians. So what is it?
A lot of pies per minute.
So what would 1 revolution per minute be in radians? 2 pi. What would 2 revolutions per minute be in radians? 4 pi. So 350 revolutions in a minute means 700 pi, right? 700 pi. You're taking this number and multiplying it by 2 pi. All right, that's what it is. So we have 700 pi per 1 minute. And that's it. Notice that the revolutions are gone, right? We're doing 700 pi radians per minute. That's how it's converted over. And this is omega. Are you all with me on that? Okay. So I think we should just use that bottom formula. Take r and multiply it times omega. R is 10 inches. And then times, all right, we're going to have to do 700 times pi. 700 times pi. And don't forget this is per minute, right? I'm going to put the 1 minute on the bottom. So multiply 10 times 700 times pi. And then there's nothing to divide by, right? Just 1 minute? So what are y'all getting approximately? What are y'all getting?